All right, welcome back. Today what we're going to do is finish chapter 18 on Gibbs free energy and entropy. The last time we talked about delta G, which is non-standard conditions, and then the specific conditions that make standard Gibbs free energy. Make sure you look at those slides like 1 atmosphere pressure for gases, 1 molar concentration for solutions, temperature, and so forth. So today what we're going to do is look at the relationship between Gibbs free energy non-standard conditions and Gibbs free energy standard conditions. And then we're going to look at the relationship between standard Gibbs free energy and equilibrium constants. So we've done a lot with equilibrium, and we know that large equilibrium constants mean the products are favored over the reactants, and very small, less than 1 equilibrium constants are mean that the reactants are favored over the products. And that is related to energy. That's related to Gibbs free energy. So we're going to look at that. So here's a new equation. So let me just do this to help you out here. At this point, what we have done is we know that delta G equals delta H minus T delta S. This is non-standard conditions. We have done delta G naught equals delta H naught minus T delta S. That would be standard conditions. We know that delta H naught can be determined from the summation of the number of moles of delta H of formations of the products minus the summation of the number of moles of delta H of formation, standard enthalpy of formation of the reactants. So we know that. We know that delta S naught can be done the same way. This is the direct method by using the appendix in the back of the book. We can look at delta S naught of the products minus the summation of the number of moles of delta S naught of the reactants. So that's how we would determine these, so that we could determine this. There is also the direct method. If you have all the delta G naughts, you can find delta G naught of the reaction from the summation of the number of moles of delta G naught of formation of the products minus the summation of the number of moles of delta G naught for a formation for the reactants. So keep these in mind. These are the direct methods. This is using the table and the appendix to find out the standard Gibbs free energy of formations or the entropies. Those are in the table. So we have one equation, we have two equations, we have these equations, and now we have a fourth equation here. And we'll have one more. So here we have non-standard conditions Gibbs free energy is equal to standard Gibbs free energy plus the RT ln of Q. And you know what Q is. We've seen that over and over in equilibrium. That's the reaction quotient. So the reaction quotient is always, it looks just like it looks just like the equilibrium expression, although it's non-equilibrium conditions, it's initial conditions. So if we're looking at a reaction like this reaction here, where it's hydrogen gas reacts with iodine solid, remember solid's not in the expression, the equilibrium expression is integrated into the constant. And then we have hydrogen iodide gas here. This is what the expression would look like. And if we know what the values are initially for in this case, the pressure of the iodine, or the pressure of the hydrogen iodide and the pressure of the hydrogen, we can plug those in and calculate Q. And then we can plug that into this equation. Knowing Q, we can calculate what delta G is. So delta G for this reaction is 4.3 kilojoules per mole per mole, it's positive, which means the reaction's not favored. All right. So in this case, this problem, and they didn't really, they had to give you this, or you calculated this. You could calculate it. You could calculate it using this direct reaction right here, doing the direct process. All right. And then you should know R. R is 8.314. They've converted it to kilojoules. That's why it's 10 to the negative third, because it's joules per Kelvin mole. We need kilojoules per Kelvin mole. We have the temperature, 298 Kelvin. We're going to assume standard temperature because we assume standard delta G here. And then we got calculate Q. So make sure you know, let me erase some of that and just make sure that you know that equation. So let's erase this. It's not going to let me do it. All right. So just make sure you know. Let me see if I can do this a different way here. Let's erase all of this just to make sure. Let's keep this part though. Let's keep that. Because I do want to point out what you need to know. Again, just a little bit of a highlight here on a couple of things. Make sure you convert this to kilojoules. That's a common mistake. Again, remember, you can't add two terms together unless the units agree. Just make sure you watch that. And then, again, equation 1, 2, and then you've got these equations, the direct method, all of these equations below, and then the fourth equation here. So those are the equations. Those are the formulas you're going to use to solve the problems in chapter 18. So let's look at a problem. All right, so it says the equilibrium constant Kp, and again, this is a typo. This should be a subscript P. So we're talking about equilibrium constant pressure that we learned in the previous chapter. For the reaction is 0.113. So that's the equilibrium constant at 298 Kelvin, which corresponds to a standard free energy change of 5.4 times 10, 5.4 kilojoules per mole. In a certain experiment, the initial pressure of the dinitrogen tetroxide is 0.543 atmospheres, and the pressure of the nitrogen dioxide is 0.122 atmospheres. Calculate the delta G, the non-standard delta G, for the reaction at these pressures and predict the direction which the reaction will proceed. If it's spontaneous, will it proceed spontaneously in the forward direction to establish equilibrium. All right, so let's dissect the problem. This is what they're asking you to calculate, and from this calculation, they want you to answer this question. So you got to organize your data. These are initial pressures, so that's telling me I'm going to be dealing with Q here. Q initial pressures. This is standard free energy change, so that means this is delta G naught for this reaction. Okay. And so they don't tell me what R is, but I know that the R I'm going to use is 8.314 times 10 to the negative 3 kilojoules per mole, Kelvin. All right. And the temperature, let's make sure we get that, 298 Kelvin. All right. So we have all the information present on this slide to solve this problem. And then the only thing we need left is we need the equation, which you're going to have memorized. Delta G equals delta G naught plus RT ln of Q. So you memorize that, and you're going to do enough problems that you should know that equation. So to me, the key is looking at the reading problem, organizing the data. Then based on the data, you should say, oh yeah, I got to use this equation, and I'm solving for delta G. So there we go. All right, so the first thing we're going to do is solve for Q, and Q equals the product over the reactant. And these are the pressures, and there's 2 moles of product formed from 1 mole of the dinitrogen tetroxide, so that's why this is squared. Again, this is stuff we learned in previous chapter. All right, so here's our equation that we've learned in this chapter. We've got the 5.4 kilojoules per mole, which was given in the problem. Here's the R that we changed to kilojoules per Kelvin mole. Here's the temperature, which is given in the problem. And then we're going to take the ln of the Q that we just calculated. And when we solve for this, we're going to do it in 2 steps. We're going to solve for everything here. And then we're going to combine it with what we have here. And so when we do that, we get an overall value of negative 3.1 kilojoules per mole. So delta G is negative. If delta G is negative, that means the reaction proceeds spontaneously. Delta G less than 0 means the reaction happens spontaneously and the reaction goes from left to right. So you can see, we calculate Q a lot of times in the previous chapters to determine if the reaction is going to go to the forward direction or the reverse direction. Well, the same thing here. With this particular Q, less than 1, that makes this term negative, which promotes that this reaction will go to the right. So what we've been looking at is usually Q less than K, and Q is less than K here, and so the reaction is going to proceed in the forward direction. And here is the thermodynamics to prove it, that delta G is less than 0, so the reaction will proceed in the forward direction. All right, so here's what we're going to do. We're going to say at equilibrium, delta G equals 0. And so we're going to, at equilibrium, so we're talking about an equilibrium process, at equilibrium, delta G equals 0. And we're going to solve for delta G naught. So that's going to be delta G naught. All this is going to be minus RT ln of K on this side. And that's what equilibrium is, right? It's when delta G equals 0. So this is the equation we get. You have to memorize that equation. So there's equation number 5 that you're going to use. Okay? So it really comes down to these 5 equations. Let's go back just to make sure that you get every one of these down. And really it's not that much to memorize because here's equation 1, non-standard conditions. Same equation, standard conditions. The advantage of standard conditions, it opens up these equations in 3 that you can calculate the standard changes based on the appendix and doing a direct calculation for those. And then equation 4 is calculating delta G from standard delta G, including the reaction quotient. And then the last equation is what happens when at equilibrium, delta G equals 0, and we can solve for delta G naught. So this is giving us another out to determine delta G naught, other than the direct method with the summations, and then the indirect, and then the other method, delta G naught equals delta H naught minus T delta S naught. All right, so you have to know equation number 5. It's going to come up. You're definitely having it on the quiz and exam. So let's look at the next slide. Oops, I jumped ahead there. So I like this slide. This slide shows you the relationship between equilibrium constant and the energy, the spontaneity of the reaction. Okay, so here you are. Here's delta G of the reactants, standard Gibbs energy of the reactants. Here's standard Gibbs energy of the products. Okay, so that's G. So here Q is less than K. All right, so the reaction quotient is less than K. We know that when Q is less than K, the reaction proceeds in a forward direction. And delta G is less than 0, which means it's spontaneous. So this reaction is rolling down the hill just like a ball rolling down the hill. And then it rolls up the hill to this part where we reach the products. And at the products, Q is greater than K. and delta G is greater than 0. So it doesn't really want to spontaneously roll up the hill that much. So then it rolls back down to get to this equilibrium point right here. At that point, Q is equal to K and delta G equals 0. So where equilibrium lies is more, is if you think a halfway is, if half of this is reactants and this is products, you can see the products are favored because equilibrium lies where the products are. All right, so delta G was less than 0, Q was less than K, reaction goes, rolls down the hill spontaneously, rolls back up, and then settles at the lowest energy, which is here, which is on the product side. All right, let's look at a different reaction. So in this reaction, the reactants are of lower Gibbs free energy than the products. So it takes effort to get up the hill here. It takes effort to get up the hill. So again, the reaction happens because Q is less than K. But Q and delta G is less than 0, so the reaction is spontaneous. The reaction does happen. But delta G is positive from the beginning to the end here. And so because of that, because it's positive, only this part is spontaneous and then this long haul here is not. So the lowest point is here, where again Q is equal to K and delta G is equal to 0. And if you think of the reaction halfway being here, you can see that the reactant is favored over the product. So when K is huge, when K is much greater than 0, then Q is going to definitely be less than K, and that's a driving force for this reaction. But when Q is much less than 1, actually I should say 1, not 0, then the reaction doesn't favor going towards the products, and here's what we see is delta G for the products are higher in energy than delta G for the reactants. So this shows you the relationship between Gibbs free energy and equilibrium constant. I would take some time and look at this, just make sure you understand what's going on here, because I like the tie-in. I like why, this is why we did equilibrium before we came back and did entropy and Gibbs free energy. All right, so in summary, if K is greater than 1, ln of K will be positive. But remember, it's delta G naught equals negative RT ln of K. So when K is greater than 1, overall this term is going to be negative and the products are favored. When K is equal to 1, ln of K is 0, delta G is 0, neither reactants or products are favored. And when K is less than 1, then the ln of K is going to be a negative value, and a negative times a negative gives a positive for delta G, and the reactants are favored. So graphically, you saw it on the previous slide. Here's a table form of what we just did. All right, so let's look at this next problem. It says, using the data from Appendix 2, calculate the equilibrium constant Kp for the following reaction. All right, so when I hear the word K, I'm going to think, okay, the equation I'm going to use is delta G naught equals negative RT ln of K. Okay, this K can be Kp, Kc, but we're going to use a Kp here. And so we're solving for this. That's what it's asking for us to solve for. And so you look at this equation and you go, okay, that means I have to know the delta G naught for this reaction. I don't know the delta H for this reaction. I don't know the delta S for this reaction. So what if I calculate the delta G naught for this reaction? And I can do that. So delta G naught equals the summation, summation number of moles of delta G naughts of formation of the products minus the summation, the number of moles of delta G naught of formation of the reactants. And I can look these up in Appendix 2. So that's the hint here. It tells you to look at Appendix 2. So here it is. Delta G naught is 2 times the standard Gibbs free energy formation for hydrogen, plus the standard Gibbs free energy formation for oxygen. Those are my products. Here they are, minus my reactant. Plug this all in. These happen to be 0 because these hydrogen and oxygen are in their standard states. And just like enthalpy, they have standard Gibbs free energy of formation is 0. So when I calculate this out, that gives me the energy, the standard energy, Gibbs free energy for this reaction. So now I know this. I know what delta G naught is. I can plug it into the equation. I know what the temperature is. The temperature is 298 Kelvin. And I know R is 8.314 times 10 to the negative 3 kilojoules per mole. So I can plug that all into that equation. Here's what we have. There's my delta G I just calculated directly. Here's my R, here's my T, and I'm solving for this. So first thing I do is divide 474.4 by 8.314 times 10 to the negative 3 kilojoules per Kelvin mole. The kilojoules per mole will cancel out, and then I divide by 298, so the kelvins will cancel out. So I get a unitless number here, equals the ln of Kp. I take the inverse natural log of both sides to solve for K by itself. So e raised to the negative 191.5 will give me this number here, 7 times 10 to the negative 84. So that's what Kp equals. And what would you say if Kp equals 7 times 10 to the negative 84? Would you say the reactants are favored or the product is favored? Well, I hope you say the reactants are favored, because that's much less than 1. That tells me this reaction, just not likely to happen. Well, it makes sense, right? Look at that delta G naught. It's so positive, super positive here. So we would expect this reaction to mostly be spontaneous in the reverse direction and not the forward direction. All right, let's look at another problem. So this is tied to solubility products. So, what we tried to learn in the previous chapter is if I add sodium nitrate to sodium chloride solution, will the silver chloride precipitate out? So we looked at this. This was a solubility. Type process, and so we would write this as solubility product. The equilibrium expression for this, or called solubility product, would be the concentration of the silver ion times the concentration of the chloride ion. And so we learned how to solve that in the previous chapter. And they tell us that the equilibrium constant for this is 1.6 times 10 to the negative 10th. And they're asking us to calculate delta G naught. So because they gave us the equilibrium constant, we ought to be thinking delta G naught equals negative RT ln of K. We have the K. We know the temperature, and we know what R is. So yes, we can solve for delta G naught. So let's do that. Plug those numbers into the equation, and let's see what we get for an answer here. Again, the most common mistake here is you've got to make sure these units are in kilojoules here so that everything works together. The units cancel out and so forth. So there we go. When we plug these in, and again, I would write this stuff out. This is how you're going to prove that you got the right answer. The kelvins cancel out, and what you have left is kilojoules per mole, which is the unit for delta G, and that's what we have here. It's 55.9, and so therefore this reaction is not favored. It's not spontaneous in the forward direction. And that's why we say silver chloride is an insoluble salt in water. Its K is very, very small, less than 1, much less than 1, and its delta G naught here is positive. All right. This last section, I'm not really interested in this. You can read it. I'm not going to test you on this, so you can read this. I don't really need to pirate this back and just kind of parrot this back and forth. So don't worry about it. You can read it if you want to. Those of you taking biology or taking biology 150, it's worth reading, because what this shows is the energy in the ATP ADP cycle, and the author did this to kind of tie in the biology with the chemistry, but I feel like it's a specialized topic. So you can read this section, but I'm not going to quiz or test on this. All right. So that's the end of chapter 18. This is part 5. So you have 5 videos to watch for chapter 18, and we'll have a test over chapters 17 and 18 on the conclusion of chapter 18. All right. Thank you.